A Moore machine is a finite state machine where the outputs of the circuit are synchronous. That is, any output values are uniquely designed for each particular state, and the only way to make the output value, or values, change is for the clock to tick and for the state to change. In this video, we'll learn about Moore machines by considering two different examples. In this first example, we'll model an elevator in a 3-story building. Each floor has a display that shows which floor the elevator is on. There's a switch that can be set at 0 to make the elevator go down a floor when the clock ticks, or set at 1 to make the elevator go up a floor when the clock ticks. This is an input variable that we'll call x. First, we have to define all of our states. We can give them state names, which are completely arbitrary. As long as they help us to determine what's going on, the name is otherwise irrelevant to the design of the circuit. S1 represents the state when the elevator is on the first floor. Because this represents the first floor, the output values y and z are 0 and 1, which is the number 1. We'll use this as our reset state. There's no particular compelling reason to select this state as the reset state in this circuit, but we need a reset state, so let's choose this one. S2 represents the state when the elevator is on the second floor. The output values y and z are 1 and 0, which is the number 2. S3 represents the state when the elevator is on the third floor. The output values y and z are 1 and 1, which is the number 3. Because this is a Moore machine, each of the output values are defined corresponding with their respective state. We can draw a state diagram for this circuit. Inside each circle is a line. Above the line is the state name. Below the line are the output values for that particular state. If there are multiple output variables, then the ordering of these variables should be defined somewhere. In this particular state diagram, the outputs are shown in order of y, then z. Then, we need to ensure that transitions between states are all well defined. We go up a floor when x equals 1 and down a floor when x equals 0. As the circuit designer, we need to decide what should happen when x equals 0, go down a floor, when the elevator is on the first floor. Let's have the elevator stay put if this condition is met. We also need to decide what should happen when x equals 1, go up a floor, when the elevator is on the third floor. Let's also have the elevator stay put if this condition is met. I will include an additional transition arrow into S1. This shows that an active low reset signal can be used to asynchronously put our circuit into the reset state, which we defined as S1. This signal will not show up in our state or transition table, but should be used as a reminder to wire up the asynchronous clear pins to an active low reset signal. Our state diagram is fully defined because we know what the next state will be in each state for every possible value of the input variable. There are no input conditions that would lead to an unknown outcome. We now derive a state table. A state table contains the same information as a state diagram, but is presented in tabular form. We have a current state column containing all of the possible states of the circuit. There are two next state columns in this example, as the input value x can take on one of two values. If the current state is S1 and x equals 0, the next state is S1. If the current state is S1 and x equals 1, the next state is S2. Continue filling this out by reading the state diagram and determining the next state transitions for the other scenarios. The output columns y and z represent the output values for each state. In S1, y equals 0 and z equals 1, and so on. Now we can select a flip-flop type and assign state assignments. Let's use a D flip-flop for this example. The state assignments are binary values that we give to each state so that we can represent them as binary numbers. We can't do Boolean algebra with alphanumeric state names, but we can do it with binary values. I like to say that state assignments are arbitrary, but they're also not. While they are technically arbitrary, we'll see that state assignments do affect how our circuit will be built. A poor selection of state assignments can lead to expressions that have more gates and inputs than a better selection of state assignments would have. The state assignment that is not arbitrary is our reset state. We should have this binary state assignment be 0 so that this state can be asynchronously entered into at any time. Each binary state assignment in this example will have 2 bits because that's how many bits are required to distinguish between 3 different states. This means our design will require 2 flip-flops. Because we selected S1 as the reset state, that state assignment will be 0, 0. Because these state assignments are arbitrary, let's have the assignment for S2 to be 0, 1, and the assignment for S3 be 1, 1. You can try out different assignments at the end of this video and see how things would change. Now we can derive a transition table. This concept is the same as what we did with counter circuits, but is now made slightly more complicated by input and output values. I consider a transition table to be a translation of the state diagram into binary values. We can't derive expressions from a state table, but can do so from a transition table. The current state column will now contain all possible values of the current flip-flop values A and B in gray code order. Because we are using a D flip-flop in this example, there is no need for a flip-flop value column, as D flip-flop values are equal to the next state values. The 0, 0 row on the transition table corresponds to S1. When we're in S1 and x equals 0, the next state is S1, and that's represented by 0, 0. When we're in S1 and x equals 1, the next state is S2, and that's represented by 0, 1. Continue this for S2 and S3. Then, fill in the output values y and z for each state. Finally, consider if the current state is 1, 0. We don't expect this condition to ever occur, so the next state and output values are don't cares. Now we can take each of the next state columns to derive next state expressions. These will be the input values for each flip-flop. Put each of the dA values into a K-map and find that dA equals xB. Then, put the dB values into a K-map and find that dB equals x plus A. Then we need to derive the 2 output expressions. These are functions of 2 variables, so I recommend using Boolean algebra instead of a K-map. Y is equal to B, Z is equal to A plus B prime. Note that in a Moore machine, the output expressions will never be a function of the input variable, only the current state values. How do we wire this up? Connect both flip-flops to a common clock source. Connect the asynchronous clear pins to an active low push button. Connect a toggle switch or other similar input device to represent the input variable. Then, using X, the value from the toggle switch, A, the output value of flip-flop A, and B, the output value of flip-flop B, connect each flip-flop input according to the expressions we derived. We also need to use the 2 flip-flop outputs to wire up the 2 output signals Y and Z. I wired this up using the 7474D flip-flop chip, a toggle switch for X, and a push button for the clock. A second push button can be used to asynchronously clear the flip-flops and put them into the reset state. I can confirm that the circuit follows the state diagram as expected. This specific example is a great use case for a Moore machine because the output has no need to ever change until the clock ticks and the circuit enters into a different state. If you'd like more practice, try designing this with different flip-flops or different state assignments, or both, and simulate it in software such as Circuitverse. As we saw in the previous example, implementing a Moore machine requires 2 sets of combinational logic. The next state logic asserts the flip-flop inputs based on the value of the current flip-flop outputs and any input variables. The output logic configures any output values to their proper value based on the current flip-flop outputs. While it's straightforward to implement this logic with AND, OR, and NOT gates, it's also possible to do so with EPROM. This is particularly useful when there are many flip-flops, many outputs, many inputs, or a combination of those. As we learned previously in the semester, using an EPROM just requires us to know the minterms of our function. We do not have to do any circuit minimization. To be clear, We can use EPROM to implement the combinational logic used with any finite state machine, including a counter or a Mealy machine. But this particular example considers a Moore machine implemented with an EPROM chip for its combinational logic. In this example, we'll consider a circuit that controls the color of an RGB LED. There are 6 states, one corresponding to each color. Each state has 3 synchronous outputs: the value sent to the red anode of the LED, the value sent to the green anode of the LED, and the value sent to the blue anode of the LED. This finite state machine has no input variable, as any clock increment will change the LED color in the same sequence. If you'd like more practice, consider how this circuit would be designed if one or more input variable could change the sequence of colors the state machine cycles through. The state table shows the current state, next state, and each of the 3 synchronous output values. Let's use a toggle flip-flop. Because there are 6 states, we will need 3 flip-flops, and all of our state assignments will have 3 bits. We can arbitrarily assign red to be the reset state, although there's no reason it couldn't be any of the other states. So red will get an assignment of 0, 0, 0. In this situation, because we're using an EPROM to implement this, state assignments truly make no difference whatsoever, but I used a gray code assignment from one state to the next. Now we can derive a transition table for this circuit. We can see the current state values, the next state values, and the flip-flop values required. Because EPROM vastly simplifies our logic, the 2 state assignments that don't correspond to used states will not be don't cares, but will go to the reset state. This will protect against random initialization in these undesired states. We can also express the value of each output variable in each state. We can decide what output pins we wish to use on the EPROM chip. This circuit requires 6 outputs, 1 for each next state expression to connect to the 3 flip-flop inputs, and 1 for each of the output variables to connect to the 3 LED anodes. Let's use Q5 through Q0. This will help us determine the hex values to program at each address in the EPROM chip. Because the 2 most significant output bits will remain unprogrammed, each of the hex values programmed onto the chip will consider those 2 bits to be high. The input values to the EPROM will be A, B, and C connected to A2, A1, and A0 respectively. All other address pins will be grounded. While it's difficult to draw a circuit diagram of a circuit containing EPROM, I can show a high-level schematic to give an idea of how this circuit can be built on a breadboard. After programming an EPROM chip, I wired this circuit up to test it out. It uses 1 EPROM chip, 2 dual flip-flop chips, and a single 7414 Schmidt inverter chip to debounce the push button to prevent switch bounce from cycling through multiple states on each button press. The footprint is likely much smaller than it would have been had I derived individual minimized expressions for each next state and output variable. In fact, I had the idea to program this on an EPROM after looking at minimized expressions that I derived for the circuit and deciding they'd be too annoying to implement with AND, OR, and NOT gates.